Today we are going to continue with the discussion we had yesterday. Yesterday we talked about potential energy, we defined it, and we also had a derivation for that. So we defined potential energy as this. Potential energy is the work done by an external force against a conservative force in moving a body without acceleration. That was important. Okay? So if I were to define that mathematically, let's do it from the perspective of electrostatic field now. Now from now on we are getting deeper into the lesson. Let us suppose there is a charge Q, okay, and a Q1, and I am going to bring a charge Q2 from some place, from position A to position B. Okay, so this will have distance R1 and this will have distance R2, and this is positive charge, and there is another charge I take which is Q2. I am going to bring it from position A to position B. So it's again, this is plus Q2. So I'm going to bring it like this to this position. So clearly, since this is positive and this is positive, there will be a force of repulsion. So the electrostatic force will act in this direction, Fe. Okay. So the Fe can be given by this expression K Q1 Q2 by R squared in that direction. But then what I'm going to do, I'm going to take this charge and then I'm going to push it against this force. I'm going to work against that force because I'm going to move it in this direction. I'm going to go from A to B. So the work I have to do must be opposite to the force. Okay. So I'm going to move it in this direction. So I would call that as my F external. Fe is electrostatic force and F external is my force. And I don't know the equation for that. I have no idea how my force is going to be. Am I going to give more force now and then less force later? How my force is going to be, I have no idea. Okay? But what do I know? I know that the kinetic energy of the body, if it remains the same at this place and also at this place, if the kinetic energy doesn't change, then the work done by me must be equal to the work done by the electrostatic force, okay, in magnitude. Yeah. If I do positive work, then the electrostatic force will have done a negative work, but then they will be equal in magnitude. So if I sum both of them up, then I will get 0 as the answer, okay? Because there is no change in the kinetic energy. So that's the most important part. Anyway, so the work done by this is a varying force, you notice it. Fe is a varying force. So the work done by the electric field is given by integral electric force Fe dot dr. This is an integral. It's an integral because it's a varying force. If this were not a varying force, it is simply F into that distance. If F remains constant, if it is uniform acceleration, then it is simply F times that distance. But F doesn't remain the same. You see, F changes with respect to distance. It will be something at R1 and it will be something else at R2 and it will be quite a different thing at every point between R1 and R2. So the force is varying. The force is not constant. So the acceleration is not constant. So I cannot just take F and multiply that with the distance. I need to go for integration because it's a varying force. So this is the work done by this. I am moving the body from A to B. So this is work done by the external force. So what do I know? If the kinetic energy does not change, that is, if there is no acceleration. If there is acceleration, the velocity will change, right? So there is no acceleration between the initial point and then the final point, then the kinetic energy does not change. If the kinetic energy does not change, then the work done by the external force must be equal to negative of the work done by the electrostatic force. So that gives you this expression minus integral A to B Fe dot dr. So the reason we are having that part, that this force must not have any acceleration, is because I have no idea how the external force is, how it changes. I have no idea. For example, I take this body here, okay, and then I'm going to lift it here. Okay, you see, this will have, I would have done some work there. Now you can see that I applied a greater force. Yeah, like that. Maybe it's varying, but then it done it. But then the kinetic energy of this body was 0 here and then 0 here. The kinetic energy does not change from initial to final. So the work done by me must be equal to the work done by gravity. So now I'll take it from the same point, from A to B again. Now this time I'm going to do it like this. Now what do you think is the work done? It's the same. Why? The kinetic energy has not changed between this point and this point, just like the previous condition. So whether I do it like this or I do it slowly like this, the work done by me is the same. Why? Because there is no change in kinetic energy. And gravity was acting down. The work done by gravity is the same in both cases, right? It was mgh in both cases. The work done by gravity is minus mgh. Minus mgh. So, in the first case I did it faster, in the second case I did it slower, and I may even do it much more slowly also. Even then, the work done by me is the same. In all cases, the work done by me is the same. And notice that in these three cases, I have applied different forces. Greater force, varying force again, and then a smaller force, and even smaller force. Okay? So that's it. So I don't have to worry about how I moved, what kind of force I applied to move the body from A to B. If it goes from A to B, then the work done by me can be measured in terms of this. If I can calculate this and put a negative sign to it, then that's what I did in all the three cases. And the work I did in all the three cases is the same, irrespective of the difference in forces and the method by which I took this body from here to that position. Okay, so that's the thing. Kinetic energy does not change, which means work done by me must be work by external force must be equal to the work done by the electrostatic force. Okay. So that is exactly what we're doing here. So this was a crux of the discussion we had yesterday. So this is about the potential energy. So this work done by the external force is called as potential energy. And when I do it for a point charge, we had this expression. This was equal to K Q1 Q2 by R1 R2 minus K Q1 Q2 right? R1. So this is what we had yesterday. It's potential energy in moving the body from A to B. And if we were to bring the body from infinity to R2, then what would happen to this term? R1 would become infinity, then kq1 by q2 by r1 will become, by infinity will become 0, because any number divided by infinity will become 0. Then the potential energy at this position can be expressed as this number kq1 q2 by r2. Okay, so simply, so potential energy at B can be written as k q1 q2 by r2, because the potential energy at infinity is 0. We define that to be 0. Okay, if that is 0, then it is simple when you move it from, so this is P, potential energy is between A and B. Okay, between A and B. Okay, so potential energy, when you move the body from A to B, okay, then you get this. And this is potential energy at B, which means that you have moved the body from infinity to B. So you get this. And then we also talked about potential. So what is potential? Potential is simply the potential energy at this point of a unit positive discharge. I am going to treat Q2 as unit positive discharge. And I am going to take that positive unit positive discharge from infinity to this position. Then what would I get? Then V at B is going to be simply K Q1, Q2 is going to be 1, right? The unit positive discharge, right? I hope this is clear to you. So this is the potential energy moving a body from A to, a charge from A to B. This is potential energy at B. In this case, what you do? Your A is infinity. Okay, in this case, your A is infinity. You are moving it from infinity to this position. So then R1 becomes infinity. Then kq1 by q2 will become 0, then you will be left only with this. Then what is this? This is potential. This potential is potential energy of the unit, of the system when you have a unit positive discharge. I told you, potential energy is for the system, it is not for any one body. It's for both, it's for the system basically. Okay, so now the other one is unit positive discharge, then this expression becomes this. So this is potential energy, this is potential. This is electric potential, electric and electrostatic, both the same, electric potential. This is electric potential energy. So electric potential is electric potential energy when you have a unit positive discharge. So Q2, when it is 1, then the value that you get is this. So and how do you get potential energy of Q2 if you know the potential at this point? Suppose I want to find the potential at this point. It's very simple. I have Q1 here. I want to find the potential at this point. It is simply kq1 by r2. This is without considering the other charge at all. And from this, I can very easily get the potential energy for any charge, just as we did for the electrostatic force, right? We defined electric field intensity as E, and then we said F is equal to simply Q into E. This is the charge that you are bringing. Previously, this charge was just 1. This E was force per coulomb. But if I bring Q coulomb, then the force experienced by this was going to be equal to QE. Likewise, this is the potential energy per coulomb, because there is only 1 coulomb charge that you are using. So, we want to find the potential energy for any charge Q, then I will say P is equal to simply Q into V. See, here I will take Q, this VB, and then I multiply by Q2, then I will get potential energy of Q2. So, the same expression. So you see, this has similarity with this one. But the only difference here is this is a vector quantity and this is a scalar quantity. So if I have a charge here at this point, I can have two numbers. One number is potential, the other number is electric field intensity. One is V, the other one is E. So if I have a charge here, I can assign two numbers at every point in space around it. One is E, that will have a direction. The other one is V. It won't have direction, but it will be a number. It is scalar quantity. So if I have a charge, if I have a point charge, at every point around it, I can have a vector quantity E and a scalar quantity V. Okay? So this is the crux of what we discussed yesterday. And if you understand it, we will go ahead with the rest of the lesson. Now we'll do example problem 2.1. Let me read out the problem. Example 2.1. A. Calculate the potential at point P due to a charge of 4 into 10 power minus 7 coulomb located 9 centimeter away. B. Hence, obtain the work done in bringing a charge of 2 into 10 power minus 9 coulomb from infinity to that point P. Does the answer depend on the path along which the charge is brought? That's the B part of the question. So, example 2.1. So, what is first asked? Calculate the potential at a point P due to a charge of 4 into 10 power minus 7 coulomb located 9 centimeter away. Let me take a charge. This is a charge Q. Okay? And I am going to find the potential due to this charge at a point P which is 9 centimeters away. So this is point P. Okay? And this is 9 centimeters, or it's equal to 9 into 10 power minus 2 meters. So what is the potential V at this point? So V at this point is equal to K Q by R. I mean, I can also calculate E. So but first I will do the V. So this is simply equal to 9 into 10 power 9. And what is Q? Q is 4 into 10 power minus 7 coulomb. So this Q is equal to 4 into 10 power minus 7 coulomb. So I am going to have 4 into 10 power minus 7 coulomb. Okay. So divided by, what is R? R is 9 centimeter, right? So that's going to be 9 into 10 power minus 2 meters. So this will give me this 9 and this 9 will cancel. 10 power minus 2 will go away. And I have minus 5 here. So 4 into 10 power 9 multiplied by 10 power minus 5, and that will give me 4 into 10 power 4 volts V. So we have not talked about the unit for potential. The unit for potential is volt. Okay. The unit for potential energy is joules. It's work done. And energy is, that is joules. But volt, V is volt. But what is volt? Joule per coulomb. Simple, right? Why? Because what is potential? That is potential energy per coulomb. Because you are bringing unit positive charge. So potential energy is joules, volt is joule per coulomb. You call that as volt anyway. Okay. So volt means joule per coulomb. So that is the potential you get there at this point. Because of this charge, the point here will have a potential of 4 into 10 power 4 volt high. Yeah? So 40,000 volt. That's the potential there because of this charge. I mean, at the same point, I can also calculate E. That's, you know it anyway, right? It's not part of the problem, but we'll do it anyway. So E at the same point, okay, I call it as V at P. So likewise, E at P is simply K Q by R square. And that would be 9 into 10 power 9 into 4 into 10 power minus 7. So divided by 9 into 10 power minus 2 into 9 into 10 power minus 2. Okay. So 10 power minus 2, 10 power minus 2 will go, then I get minus 3 here, and then the 9 and 9 will go, you get this here. So what would I get? My E is going to be equal to 4 by 9 into 10 power 9 minus 3 is 6. Okay, so this is going to be Newton per coulomb. That would be my E. So at the same point P, I can have two numbers. One, the voltage, and then the other one is the other one is E. But E will have direction also. E will have a direction. Okay. So I'm not this direction, the direction of R. Okay, I'll say this R direction. Vector. That's magnitude. So that is part A of exercise 2.1. So this has not been asked, but we've just done that. So the point here is that given a charge, you can find voltage and electric field intensity, electric potential and electric field intensity, V and E at this point. The E value will be this at this point, and the V value will be this at this point. Okay. So then what's the second part? The second part is hence obtain the work done in bringing a charge of 2 into 10 power minus 9 coulomb from infinity to the point P. Okay. Now you are going to bring a charge of 2 into 10 power minus 9 coulomb from infinity. So we know that, right? So what it is, so its potential energy is equal to V into Q or Q into V. Now you see V is joule per coulomb, so you need joules. So that is energy is equal to potential into Q. We did that a short while ago, right? P is equal to V into Q. V you already know. This is 4 into 10 power 4 volts. And what is the new charge that you are bringing? Instead of unit positive charge, you are bringing 2 into 10 power minus 9 coulomb. So that would be, Q will be 2 into 10 power minus 9. Okay, so many joules now. This is joule per coulomb and this is coulomb, so we will get joule. So 8 into 10 power minus 5 joules. Okay, so that's the answer. So this is the potential at this point, and if I bring this charge 2 into 10 power minus 9 to this point, then the amount of work I need to do is this 8 into 10 power minus 9 joules. Okay. The other question that is asked is this. Part of it is this. Does the answer depend on the path along which the charge is brought? No. I mean, what it means is that should I bring it from infinity like this, or should I bring from somewhere infinity like this, or should I bring from here this way, or should I make an arc and then bring it here? Does it depend on the path along which you are bringing this charge? No. Why? Because the electrostatic field is a conservative field. In a conservative field, the potential does not depend on the path you take. The potential difference between 2 points will not depend on the path you take. Okay. That brings us to the discussion of conservative fields. Okay, we'll discuss that now. So what is a conservative field? Okay, you have fields. You have gravitational field. You also have electric field. Or you have magnetic field, and there could be other fields too. Okay, maybe a nuclear field over a short distance. Anyway, so if you take these fields, for example, you are calling them as conservative fields. The reason is this: if I take a point here in the field, let's suppose it's gravitational or electric field here. This is all electric field. Okay, if I take a point here, the amount of work I am going to do to go from this point and then to come back will be 0. If I come back to the same point, let's say this is point A. I start from this point, I go somewhere, and then I come back to the same point. Then what is the net work I would have done? The net work I would have done would be 0. That's the idea. Okay, the net work for me to make one full round is 0. Okay. So what does it mean? So the work done, okay, to do a loop, to come back, to start from point A and then to come back to the same point is actually 0. So that is the definition of a conservative field. So you take a point, make a circle or make a round, you make a loop, you come back to the same point. What's the next amount of work you have done? 0. Okay. So this gives us other inferences. Suppose there is a point B here. Now B here. I go from A to B via this. Okay, so I should do some work and say W A to B. To go from here to B. And then from B to E, I'll do the work. I'll call this as W B to E. So what is WA? So work done when I went from A to B plus the work done when I went from B to A. So what is that? So WA must be equal to the work done WAB plus WB. But we know in a conservative field, this work done must be equal to 0 because we are starting from point A and then coming back to the same point. So this must be equal to 0, which means WAB must be equal to minus WB. Okay. So let me take another path of doing this. Okay. That path will have the same line this, but this time when I come back from B to A, I'm not going to come back to this path, but I'll take this path. Something like this. So this is my second path. Okay. So this also will have some work, right? B to A. This work I call as WB dash. Okay. This is WBA. Then I take this path as BA dashed path, and the work done in that path is WBA dashed. But even in this case, what do? I start from A, I go to B, and then I take another path and then come back to the same thing. So in this process also, I cannot have any network done, right? That is obvious because I start from point A and then I come back to the same point. So here also I should not have done any network. So which means WAB this path plus WBA dash, this is this path, WBA dash equal to this path. This should also be equal to 0, which means WAB is equal to minus WBA dash. So I'll call this as 1 and I'll call this as 2. So WAB is equal to minus WBA, so WAB is equal to minus WBA dash. So the work done in this path must be the same as the work done in this path. Okay? So you can see clearly that the work done does not depend on the path, it's going to be the same. Whether I take this path, or if I take this path, or if I just go like this, it's the same. So the work done depends only on initial and final positions, not on the path you have taken to go to those positions in a conservative field. This works because of the definition. What's the definition of conservative field? If you take a point, you go from that point, then you come back to the same point, then you complete a loop, the net work done must be 0. You should not do any net work. That is the definition of a conservative field. And if that is the definition of a conservative field, then you can clearly say that the work done between point A and B will be dependent only on those 2 points, but not on the point, not on the path you have taken to go from A to B or from B to A. Doesn't matter at all. It should be the same. Okay? So, electrostatic field is a conservative field. In a conservative field, the work done between 2 points depends only on those 2 points, not on the path you've taken to go from one point to the other point. Okay? Whether I take this path, and this path, and this path, and this path, I would have the same work done. Okay? So, to answer that part of the question, no. The work done, or the potential energy, does not depend on the path you've taken. So, whether I go from this infinity to that point, or from that point, that infinity to this point, or whether I make a circle and then come to this point, doesn't matter at all. The amount of work I do will be the same in all cases. That's it. Hope it's clear to you. What the potential due to a point charge is at a point. Let us see what would be the potential at a point due to a system of point charges. We have done something similar in the case of electric field intensity. We are going to do the same thing for potential here. Let me say that I have a few point charges here. So this could be Q1, and this could be Q2, and this could be Q3, and this could be Q4. Let's say I have 4 point charges, and each point charge will set up a field around that, right? So we know that, and each point charge will also have a potential at each and every point around itself. So what we're going to do now is that we're going to find the potential due to this system of charges at any random point, and that point is P. So at this point, what would be the potential due to this system of charges? So the system has 4 charges, 4 point charges, and what should be the potential at this point? What is Vp? That's the question. Well, I can say that there would be a potential due to this charge, Q1, and there would also be a potential due to this charge at this point, Q3, and then Q2, and then Q4. So Vp must be the sum, the algebraic sum of all the potentials. Note that potential is a scalar quantity, it's not a vector quantity. So what did we do in the case of electric field intensity? We took E1 due to Q1, and then E2 due to Q2, E3 due to Q3, E4 due to Q4, and then we added them vectorially because E's are vector quantities, but V's are scalar quantities. So you don't have to do the vector addition for V. Okay, so Vp will be equal to the potential due to Q1 at P. So I will say that is V1P, and then again it's potential at P due to Q2, so V2P, then potential due to Q3, which is V3 at P, plus potential due to Q4 at P, which is V4 at P. So if I add these 4 voltages, then that should give me the net potential at this point. Okay. So what is V1P? So V1P is what? It's potential due to Q1. So let's say this is the distance R1 to P. So what is V1P? V1P would be K Q1 by R1P. I can also find E1 due to Q1, right? That it's not needed now, but I'm just saying, if you just want to do that too, then you can say E1P is equal to K Q1 by R1P the whole square. Then you will have a vector, right? So you will have R1P unit vector in this direction, right? So this will be your E1P. You will have vector. But right now we are not focused on that. We are focused on this. We are not focused on this. We are focused on this one, potential. So then what is the potential due to Q2? That is V2P. That is equal to same K, then Q2 divided by R2P, the distance from Q2 to P. That is R2P. R2P. That's a potential. And if you want to find E, then you can find E2P also for that. I'm not going to do it. So V2P. And then V3P. So what is V3P? V3P is equal to say K Q3 by R3P. So this is Q3. This is going to be R3P. So that is the potential here. And then what is V4P? K Q4 divided by R4P. So Q4 is here, P is there. So this is going to be R4P. But these are all scalar quantities, right? So if Q1 is positive, then I will have positive value here. Suppose Q2 is negative, then I will have negative value here because K, then Q2 will be minus Q2, then R2 will be negative value. And then if Q3 is positive again, then I will have Q3 by R3P. Suppose Q4 is negative, then I will have a negative value here. But I can just add them up like numbers. They are scalar quantities, so I can just add them up. So what is the net V potential at point P? So Vp is equal to V1P plus V2P plus V3P plus V4P. So that will give me K Q1 by R1P plus K Q2 by R2P plus K Q3 by R3P plus K Q4 by R4P. Well, I can generalize this result, right? So I can start from Q1 to Qn. I can have n number of charges. We have done it for 4 charges here, Q1, Q2, Q3, Q4. But I don't have to stop with 4. I can go up to say 1000 charges and 1 million charges, 1 billion charges. I can go to n number of charges. So if I do that, then Vp can be written as Kq1 by R1P plus KQ2 by R2P plus so on plus KQN by RNP. N could be any number. Okay. And as we did in the case of electric field, we can do the same thing here too. I mean, we can use a symbol to represent this, the summation symbol, right? So how do we do that? That's very simply Vp is equal to K into sum of I tending from 1 to n, right? So Qi by Ri. So this is the general result. We have discussed the symbol already. This is sum, it's the summation symbol, sigma. So that this is the short way of writing the entire n terms. Instead of writing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then say maybe the nth term, you are going to write it in one single term. So this means, this summation means this. Sigma I is equal to 1 to n Qi by Rep means Kq1 by R1p plus Kq2 by R2p, then Kq3 by R3p, all the way up to Kqn by Rnp. So that is what this notation means. So this is how you find the potential at point P due to a system of charges. It's a potential at point P, a potential at a point due to a system of charges. So what are we doing here? You have a system of charges. Let's not worry about how you put that system together. Let's not worry about it. Suppose you have a system. There are n number of charges in this. Then because of these charges, what is going to be a potential at this point? Suppose I have a set of charges here. What would be the potential at this point? And each charge will contribute to the potential. So I need to take the potential from each charge and add them all up. That is exactly what we are doing here. We did it with 4 charges. I can go to any number of charges. And when I do it for any number of charges, this would be the general equation for it. Oh, that's great. The next idea is this. Potential energy of a system of charges. If you just write that down. Potential energy of a system of charges. So what have we done? Just a short while ago, we did this. We found the potential at a point due to a system of charges. So you have a system of charges, and then you're trying to find the potential at a point due to this system of charges. But that is different from what we're going to do here. So what is this? This is potential energy of a system of charges. Well, what is the energy that you have to spend to put even the system of charges together? Okay, once you put the system of charges, you can find the potential due to the system at a particular point. That is all right. That's what you've just done. But then, how did you first of all put this thing together? What's the amount of energy you spent in putting these 4 charges or a number of charges together? That's the first question. Okay. So, what was your system of charges? You had Q1 here, and then Q2 here, and maybe Q3 here, and then Q4 here. So this was your system of charges. But how do you first of all put the system of charges? That is this. But once you have put the charges, finding the potential due to the system was done a little earlier. It was done before this. That's what we just discussed. But this one is the energy involved in putting the system together. Okay, I want you to understand the distinction between the first one and then the previous one and what we are doing now. Okay. Okay, so we'll try to do it. So clearly, how do you put these four things together, or n number of things together? First of all, let's start with the first Q1. Okay. So what would it do? Okay. When I bring, there is no field, there is no electric field, nothing. Okay. So when I bring Q1 from infinity to this point, what is the amount of energy that I would spend? Nothing. Why? I brought Q1 here. Why? Because there is no conservative force already. So you are not going to do any work against that force. Okay? So you will not spend any energy to bring it to that position. There is no external work you need to do against a conservative force, because the conservative force is not there. So there is this field, this empty, there is this space, empty space, then you are bringing the charge from infinity to that, to a particular point in that space. You are not going to do any work at all. So to bring Q1 from infinity to this position, you don't have to do any work because there is no field there. Okay? So work done in bringing Q1, let's say work done in bringing Q1 is equal to 0. From Q1 from infinity to this position. I'll call it as W1 infinity. Okay, so from infinity you are bringing Q1. You are not doing any work at all. So the work done is 0. Because there is no field present already. Okay, that's the reason. But what happens when you bring Q2? Okay, now we are going to bring Q2 from infinity to this place when Q1 is already present. So when Q1 is already present, then there is a field already there. Now you are bringing Q2. When you bring Q2 to that place, then what happens? You have to do work now. You have to do work against what? You have to work against the field due to Q1. When you brought Q1, there was no field. But you brought Q1 already. And now you are bringing Q2 from infinity to this position. Let's say this is a position of Q2. So you brought it from infinity to this position. So you have to do work. So what would be the work done? The work done in bringing Q2 from infinity to position 2 is equal to what? K Q1 Q2 by this one, right? R12. Because from infinity to this position you are bringing. So we have derived that already, right? So K Q1 Q2 by R12. So that is the amount of work you need to do to bring this. Now let me take Q3. So when I bring Q3 to this position, now you see I have to work against two forces. One force due to Q1, and the second force due to Q2. Right? So I have to do work against the Q1 field, and I also need to do work against Q2 field, because you see, suppose I bring Q3 to this place. So Q1 has already set up a field there, and then Q2 has also set up a field there. So I need to do work against the resultant field, right? So how do I do this now? I'll say work done in bringing Q3 from infinity to position 3 is equal to work done against the field due to Q1 plus the work done against the field due to Q2. I have to work against this, I also have to work against this, right? So that is what I am going to do now. So this is going to be K Q1 Q3 by this distance. This could be R13, R13 plus this one, K to Q2, Q3 by R23. Okay. Then what about the fourth one? Let's say I bring Q4 here. Again, I am bringing it from infinity to this position. Now, this has to work against three fields. Field due to this one, Q1, field due to Q2, and also field due to Q3. So now, work done due to work done in bringing Q4 from infinity to position 4 is 4 infinity is equal to K. Now, work done against this field, Q1 field, right? So, K, Q1, Q4 by now R14, R14 plus then Q2 against Q2, right? So, K, Q2, Q4 by R24. This will be R24 and plus this one. Okay? It will be R34, right? This one is R34. So K, Q3, Q4 by R34. So even to set up this system, I need to spend so much energy. When I bring the first one, it's nothing. Okay, I'll spend no energy because I'm not doing work against any field at all. But then once I put Q1 there, the moment I bring Q2, then I have to do this amount of work. Now once I put these two in place, when I bring the third one, then I have to do this amount of work against first one and then the second one. And once I put all these three things in place, when I bring the fourth one, then I need to do work against Q1, Q2 and Q3. So I'll have the three terms. So the total work that I do to put this system together is a sum of all these individual work done, individual energies, right? So basically the work done, total work done is equal to W1 to infinity plus W2 to infinity, infinity to 2, W infinity to 3 plus W infinity to 4. Okay. So if I add them all up, so this is going to be 0, this is going to be K Q1 Q2 by R12 plus K Q1 Q3 by R13 plus K Q1 Q4 writing this way, Q1 Q4 by R14, okay, plus I'll do the second one, K Q2 Q3 by R23 plus K Q2 Q4 by R24 plus K Q3 Q4 by R34. So this would be the sum. So if you ignore this 0, then I can write this W as the rest of the things. Okay. So I have 1, 2, 3, 4 charges here, and then you see 1, 2, 3, 4, 5, 6 terms that will help me do that. Okay. So if I have more, if I have the fifth charge, then I'll have another 4 terms added to that. Okay. Because there will be work done against Q1, Q2, Q3 and Q4. See, the order in which you bring the charges doesn't matter at all. Okay. I can first bring Q3 and then Q1, Q2, Q4. Even then I will have the same equation. If you do it, you can do it and then figure it out yourself actually. Or I can have Q4 as the first charge and then I can start bringing Q3, Q2 and Q1 later. Then when I sum it all up, I will get the same result. So that doesn't, the order in which you bring the charges, that does not make any difference at all. It is not necessary that you should bring the first one, Q1 first, and then Q2 second, Q3 third, and then Q4 fourth to have this equation. I can bring them in any order. I can bring Q1 first, and then Q4 second, and then Q3 and Q2. I can bring them in any order and have the same equation. Okay? So this is the amount of energy I need to spend to put this system in place. But once the system is in place, I can find the potential due to this system at say some point A, P. That's what we did prior to this. Okay. So you need to understand the difference between this derivation and the previous derivation. This is putting the system together, a system of charges together. Okay. So there's a potential, you require potential energy to do it. And once you have put the system in place, you take a point and then see what would be the potential at that point due to the system. That was the previous one. Hope it's clear to you.